Hello everyone, this lesson is going to be on renewable energy sources, and the primary focus here is going to be on the production of electrical energy using various different sources. So I'll start off with a few definitions. First of all, just defining renewable versus non-renewable energy sources. I also have in brackets here alternative. So renewable would be the alternative to traditional sources for generating electrical energy, and that would include typically the burning of fossil fuels like coal and natural gas. So non-renewable energy, so these are energy sources in which we have a limited or a finite supply. And what that does mean, of course, is that eventually we are going to run out of those resources. So they cannot be replenished, at least they cannot be replenished in a short period of time, which means over the course of years, decades, or centuries. So some examples of this would include, as I mentioned, fossil fuels. So here in Alberta, in fact, most of our electrical energy is still generated by the burning of fossil fuels. So that has been in the past primarily coal. We're slowly transitioning over to the burning of methane in order to generate electrical energy. And we'll see that we're seeing a lot more of the renewable forms of energy. But still, yes, here in Alberta, most of our electrical energy is generated using non-renewable resources. Renewable energy, so these ones here we have essentially an infinite supply, which means that these ones we're not going to run out of these ones, at least not anytime soon. Sources can be replenished on a much shorter period of time. So examples of these, and this is going to be the main focus of this presentation, would be on things including solar energy, tidal energy, hydroelectric, wind energy, and biomass. So everything is relative. So non-renewable energy sources, the fossil fuels, they do come from fossils, from plants that did die millions and hundreds of millions of years ago. So yes, they can be replenished, but not on a human timescale. And that is why we do say that there is a finite supply. In terms of renewable energy sources, most of these, not all of them, but most of them, do rely upon the energy coming from the sun, solar radiation. And because we do expect our sun to be around for several billion years still, we can pretty much say that we're not going to run out of this energy source. And the final term that I have down here, which is important for Science 30, sustainable development. Development which meets the needs of the present without compromising the ability of future generations to meet their own needs. And here again, the primary focus is going to be in terms of accessing energy. So what are the advantages of renewable forms of energy? So we're going to go through a whole bunch of these, and I will also talk about biomass. So these are going to be the advantages for all of these renewable sources of energy, except for biomass. That one is going to be a little bit different. So the first one here is, yes, as we already saw, they are renewable. So we have essentially an inexhaustible supply of these energy sources in order to generate electrical energy. There are no fuels and there are no fuel costs that are associated with them, and they are non-polluting. So there may be some pollutants that are created when they're coming up with the technology, developing the technology, but in terms of emissions that we see when electrical energy is generated, what we don't see are these chemical pollutants, including carbon dioxide. Remember, that is the major greenhouse gas, which is responsible for what most argue is the greatest environmental issue that we have today, which is climate change. So there are other greenhouse gases, but certainly CO2 is the main one that we do focus on. So through the burning of fossil fuels, whether it is coal, oil, or natural gas, there is CO2 that is released into the atmosphere that is contributing to this greenhouse gas, the greenhouse effect, and global climate change. We've also seen in the chemistry unit the SOx and the NOx as well, pollutants also generated typically through the burning of fossil fuels. And uranium in nuclear reactors, that is also a non-renewable energy source. Yes, we do have a longer supply they do predict than what we do have for fossil fuels, but eventually that one is non-renewable as well, the uranium, and we will eventually run out of that one. And of course, with that, there is radioactive waste that is generated, and this radioactive waste, it doesn't just stick around and create problems for biological organisms for a few years. It sticks around for, they believe, thousands of years and can create problems for thousands of years. In other words, we need long-term storage for that radioactive waste. So another advantage of renewable energy sources, fossil fuels and uranium, these are really important energy, concentrated energy sources that we have. And if we could switch over to renewable sources of energy to generate electrical energy, that would conserve some of the fossil fuels and allow them to last longer, allow them to last for not just us, but for future generations as well. And right now, we can certainly use alternative energy sources for generating electrical energy, for vehicles, for electric vehicles, but still some significant issues in terms of air transport, for example. And right now, really, fossil fuels is the only solution that we have for air transport. So we'll start off with geothermal energy. So geo is referring to the earth. Thermal is talking about heat energy. So when the earth was initially formed 5 billion or so years ago, so the story goes, it began as a spinning nebular cloud, which was eventually pulled together by gravity, eventually forming the molten, very, very hot liquid molten earth. And since then, the earth has been cooling off, but even though it has been cooling off, the Earth does generate its own thermal energy through the radioactive decay of elements that we do find in the Earth's core. So we're taking a look at it here, picture of the Earth and cutting into the Earth. So of course on the surface, what we do have is the crust, which is solid. But as you go deeper and deeper down, it does, as we will see, get hotter and hotter, going through the mantle, the outer and the inner core. And then what we do have is the liquid molten below the crust of the Earth. So very, very hot temperatures, and we'll see that there's the potential that we can tap into this geothermal energy and use it to generate electrical energy. So yes, it is the radioactive decay or degeneration of radioactive isotopes within the Earth's core underneath the crust of the Earth that is generating and slowly releasing this thermal energy. So this pie wedge that we're taking a look at here shows the temperature of the Earth as we go deeper and deeper down in kilometers. So 2,000, 4,000, 6,000 kilometers below the surface of the Earth, we can see that the temperature is going to be getting, well, really, really, really hot. Hundreds and thousands of degrees Celsius. This is the general pattern that we see, is that for about every 100 meters that you go down below the surface of the Earth, the temperature increases on average about 3 degrees Celsius. So hotter and hotter as you go deeper and deeper down below the surface of the Earth. We can see this visibly on the surface of the Earth as well at the boundaries between different tectonic plates. So we do know that the crust of the Earth, the surface, it is made up of all of these plates that do shift around. And at the boundaries between these plates, this is where we can have the sliding of one boundary past the other, where we can have one going up over top of the other one, and where we can have the colliding and the pulling apart of these plates. So this shows many of the plates that do make up the Earth. And if we just kind of focus on this one here, the Pacific Ocean, the Ring of Fire. So all of this big, large chunk that we see here, it is referred to as the Pacific Plate. And all around the boundary, we have these other plates. So for example, close to where we are, we have the North American Plate. We have the Juan de Fuca Plate. other side of the Pacific, Philippine plate, the Australian plate. So all of these plates, again, they're interacting with each other in various different ways. The sliding, the colliding, the subduction, all kinds of different possibilities. And when this does happen, we can see the release at the surface of some of this geothermal energy. So it is called the Ring of Fire because it's around this boundary that we see a great deal of volcanic and also earthquake, tectonic activity that is taking place at these boundaries. And this is sort of a classic example where we do have a volcanic eruption and where we do have lava that is escaping at the surface. So this is molten that is coming from deep down below the surface of the Earth, which would be thousands of degrees Celsius. So then the question is, this is a form of energy. Can we somehow tap into this very, very hot temperature and use it to generate electrical energy? So I'll just remind you about in nuclear reactors and also in fossil fuel reactors that are generating electrical energy, more or less what is happening is we're burning fossil fuels or we're using uranium in order to boil water, create high pressure steam, and that high pressure steam is used to turn enormous turbines and generate electrical energy. So is there some way that we can tap into this very, very hot geothermal energy and use it to turn turbines and generate electrical energy as well? Well, there are some other possibilities as well before we get into the generation of electrical energy. This is kind of close to home. This is very close to the Banff town site. This is the Upper Hot Springs, and the heat within this water here, somewhere between about 40 and 50 degrees Celsius, typically does come from geothermal energy. So it works something like this. So in this picture here, it has the rainwater, but it could be snowmelt as well, kind of percolating down into the porous rock, eventually reaching very, very hot temperatures, many, many hundreds or even thousands of meters below the surface of the Earth. So as that water does heat up, not only does it form hot water, but it can form steam as well. And eventually, in the case of the hot springs that we have not only in Banff, but all throughout Western Canada, especially British Columbia and the western part of Alberta and the western United States as well, many, many, many hot springs. So that's not steam, but it is hot water that is eventually coming up and allows us to enjoy those hot springs like in Banff and Jasper and many others that are fairly close by. But can we use this to produce electrical energy? So in this picture at the top here, we do have a power plant. So that is the electrical energy generating station, and we can see sort of the power lines here as well. So how might this play out? How would this work? Well, we know that it's really, really hot the deeper down we go. So can we take water and inject that water, actually pump it down from the surface to where we do have those very hot temperatures? So here it's not going that terribly deep. It's only reaching temperatures of about 200 degrees Celsius. But of course, water boils at 100 degrees Celsius, at least at sea level, and is converted into steam. So that steam takes up more space, it expands, more volume, more pressure. So then what we would have is coming up is high pressure steam. So just like in a traditional electrical generating station using fossil fuels or a nuclear generating station, same principle, we have high pressure steam. So then in this power plant, we would have these large turbines that are being turned by that steam and generating electrical energy. So that would be really nice if we could do that. This is just showing one of these turbine generators, electrical generator. And again, it is the steam that would be coming in that's allowing these turbine blades to spin and eventually convert that into electrical energy. Unfortunately, as we'll see, there aren't a lot of places around the world where you can actually do this. So if we take a look at the power plants that I'm showing on this picture here, where they're located is at these tectonic plates. So if we take a look at all of these along here, these ones over here, they are all around that ring of fire where this geothermal energy is very close to the surface of the Earth. That's not so much the case where we are right here in southern Alberta. But that doesn't mean we still cannot use this thermal energy for something else, the geothermal energy. So even if we couldn't use it in Alberta to generate electrical energy, the temperatures may not reach high enough temperatures to convert that water into steam, we can still increase the temperature of water by pumping it down below the surface, having it circulating back up, and we could maybe use it for things like keeping greenhouses warm in the winter time above 0 degrees Celsius. We could use it for aquaculture. It can be used for in-floor heating. So in this picture here, it looks like this is outside, that this is a driveway or patio. And what we have is this PVC or plastic tubing that's going through the concrete. And what would be circulating through that tubing would be ethylene glycol or some sort of antifreeze that would be at a very, very high temperature. So at that very, very high temperature, that might be enough to melt any snow and ice that's on this, we'll call it a driveway, and then you wouldn't have to shovel your snow in the winter time. It could also be used for in-floor heating inside of a house. So same sort of idea here. We're taking a look at this house that's under construction, and before they either pour the concrete floor or put finished floor on top, what we have is this, again, PVC tubing that's weaving its way through the subfloor here essentially, and you would have a liquid that's circulating through there at a very hot temperature that would then be releasing that heat into the room and keeping the room warm. So this is how it would work. We would need to somehow pump that liquid down below the surface of the earth, various different designs that they show here. And of course, the deeper down you pump that water, the hotter the temperature is going to reach. But even pumping it down a couple of hundred meters would allow that water to be returned much, much higher than 0 degrees Celsius. And that would certainly make for a much more comfortable environment and save electricity or fossil fuels that are used to heat homes in Alberta currently. So disadvantages of this, well, the major one really is that there truly are very few usable sites around the world where we can use geothermal energy and convert it into electrical energy. It would need to be very close to the surface and typically very close again to where we have those plate boundaries. And as we'll see with many of these, actually building the construction of a geothermal facility for generating electrical energy, huge cost associated with that sort of thing as well. So the next one here is solar energy. So here, of course, we're talking about with solar energy, the energy that is coming from the sun. And in this case, keep in mind that energy coming from the sun, it covers a whole bunch of different wavelengths and frequencies of energy. Much of it is blocked out by the Earth's atmosphere, but we certainly do have the visible form of light that reaches the surface, infrared radiation, heat radiation that reaches the surface of the Earth, and some of the ultraviolet radiation that also reaches the surface of the Earth. So in the case of the solar energy, the solar panels or photovoltaic cells that we're taking a look at here, it is the visible light. It is the light energy that is being captured by the photovoltaic cells. So this term here, photo, is referring to the light energy, visible light that is coming from the sun, and voltaic, what these panels are doing is they're actually directly converting light energy into electrical energy. So very, very nice. Only one energy transformation that is involved here and very little loss of energy that does take place. So quite an efficient process. So overall, this is what's going on. We do have glass plates that are involved. That is the photovoltaic cell. Without going into all the details here, they just sort of outline two different layers of the glass. Silicone is the glass. So at the top here, they have the N-type silicone. At the bottom, they have the P-type silicone. And what's happening within the silicone is we're going to create a charge difference. We're going to create polarization where we have negative charges at one side and positive charges at the other side. So as soon as we have the separation of the charges, the electrons do want to move. They want to move from where there are more electrons to where there are a lack of electrons. So as I have written down at the bottom here, when light strikes the photovoltaic cells, we do have negatively charged particles that are produced, and of course those are electrons, and in this case it's from phosphorus in the photovoltaic cells, and positive charges that are generated, essentially electron holes here from boron in the photovoltaic cells. So if we go back up to the picture, what they're kind of saying is at the top it ends up being negatively charged, at the bottom positively charged. So those electrons, they now want to move. So very similar to a battery, you have the separation of charges, and if you have a conductor connecting these two sides, that will allow the electrons to flow. So in this case, electrons are going to move, and then we can use the movement of those electrons in order to generate, or that is, electrical energy that can be used to turn on and run electrical devices. So yeah, simply connecting the two sides is what is going to allow the electrons to move, and that of course is current that we do have once those electrons are going through the conductor. So in this case, that is going to be direct current that is generated as opposed to alternating current. There are other ways that the energy from the sun can be used as well, besides generating electrical energy. So just a couple of other quick examples here. Passive solar heating. So here we do have a house with a whole bunch of glass windows, and all this is doing is allowing light energy and the heat energy to come in. And as with a greenhouse, light can pass through, and then it's converted into longer wavelengths, which are not able to escape. So as long as we have all of these glass panels here allowing the light to come in, that can be used to passively heat up this house. Active solar heating. So in this case here, what we do have instead of the glass windows, we have a whole bunch of black tubes. And black is an absorber of energy, and there's a fluid inside of these tubes that's going to be heating up. So if you can use all of these tubes on the surface of the house, in this case it's the roof that we're taking a look at that's being heated up, and then that fluid inside of the tubes could be circulated through the house, perhaps through the in-floor heating, and used to heat up the house. So no energy conversion taking place here in terms of light energy into electrical energy. It's just directly using the heat energy from the sun in order to heat the house in this case. So disadvantage of the solar energy, well, of course, the sun doesn't shine 24 hours a day. And if you live in a polar region, like in Canada, it's wonderful in the summertime where we have much, much more daylight. But during the winter time, not nearly as much sunlight. And because the sun is so low on the horizon, not really the most efficient process in southern Alberta during the winter time. Great in the summertime, but not so much in the wintertime. Cost. There is a significant cost associated with the production of the photovoltaic cells. Costs are going down all the time, but here in Alberta, still much, much cheaper to generate electrical energy using other sources. There is a large surface area of land that is also required in order to set up all of these solar panels in order to generate a sufficient amount of electrical energy. And although I don't have it here, there is no pollutants, chemical pollutants that are generated by using solar panels, but that doesn't mean in the production of solar panels that there aren't some chemical wastes that are generated, and yes, that is the case. Next one I have here is tidal energy. So this picture here actually shows a wave, not so much the tides. Waves are generated by the winds, but tides are generated by the gravitational pull from both the moon and the sun. So not exactly the scale here, but the sun is huge, 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 huge compared to both the Earth and to the moon. So the larger the object, the greater the gravitational pull. However, the moon is much, much closer to the Earth than the sun is. So because of that, most of the gravitational pull and the tides does come from the moon and not the sun. It is both, but it's a greater impact than the moon than from the sun. So when we do get the higher tides, and you don't need to worry about all the language here, but the higher tides are the one down at the bottom here that we call the spring tides. The lower tides or smaller tides are what we call the neap tides. So when we get the higher tides is when we get the sun, the moon, and the earth that are all lined up in a straight line. So that could include the moon that's in between the earth and the sun, or it could be the moon over here as well. So when we have either a full moon or a new moon, that is when you do get the biggest tides. And that's what it's trying to show in this picture here. So it's showing the earth, and then on the outside, it's showing the tides generated by the sun in yellow and by the moon in blue. So when we get the biggest bulge, the biggest tides is what they're trying to represent here, is when we have the moon, the sun, and the earth that are all lined up in a straight line. If we have the moon, the earth, and the sun that are going at right angles to each other, this is when we get the smaller tides, and those again are the neap tides. So yes, you should keep in mind, and you should recognize pictures like this, which one will give you the larger tides when the sun, the moon, and the earth are all lined up in a straight line. And that's what it's showing in this fairly simple animation here. Again, don't worry too much about the actual terms, the spring tide and the neap tide, but if you take a look at the picture in the middle, when we see the bulges, the bigger bulges on either side, that is representing the larger tides, and that is when we have the sun, the earth, and the moon, either in this location, large tide, or this location here, a large tide. So to produce electrical energy, and again, there aren't a lot of great places around the world where you can do this, but what you do need to have is a dam or a barrage that's going across an inlet or a bay. So in this picture here, it looks like maybe the sea or the open ocean is at the upper left-hand side, and the bay, estuary, or basin is at the lower right-hand side. So this picture that we're taking a look at here is showing how it would work. So this is the barrage or the dam that's going across that basin that they're calling it here. And this is the open ocean or the sea at the left-hand side. So when the tide is high, when the tide goes up, then these gates, sluice gates in the barrage, they would be open and they would allow the water to flow into the basin. Then they're going to close off the gates, and then the level in the sea is going to go down over the next few hours. So now what we've done is we've held the water in the basin at a higher level. So what we have is gravitational potential energy, and where it wants to go is to the lower level. But the only way that it can get there is by passing through this turbine. So we open the gate, allow the water to pass to the lower level. That's going to turn the turbine, this turbine connected to an electrical generator, and that would generate electrical energy. But of course, this is only going to happen as long as you have the water at a higher level in the basin than what it is in the sea. In fact, we can have this working in both directions. So we can close the gate, close the sluice gate when the sea level is going up. And then once it reaches its maximum height, open up the gates, allow the water to pass through the turbine into the basin, the bay, or the estuary, turning the turbine and generating electrical energy. Then once the levels are the same, close the gates again, wait until the sea level drops down, and once it's at its lowest level and it's still higher within the estuary, open up the gates again, and allow electrical energy to be produced. So this is only going to happen twice throughout the cycle, and it's not continually generating electrical energy. There are some other possibilities that they're looking at, and these ones here, they're called marine turbines. So in this case, it's not closing off or blocking off an estuary or a basin. When we do have the movement of the water back and forth, it would then turn these turbines that are connected to electrical generators, and we can see these cables here that are then going to be going to the shore that would carry that electrical energy. So not quite as disruptive on the environment as having a dam that is going across a bay or an estuary. But if that is the case, yes, there are very, very few good locations around the globe. The one of the best in the world where we have the greatest difference between the high and the low tides, in fact, is here in Canada, in eastern Canada, the Bay of Fundy. But yes, electrical energy is only produced for short periods of time, and that's only when the tide is changing. Constructing these does disrupt the aquatic environment and the shoreline ecosystem, and really, really high construction costs that are associated with generating electrical energy this way. Wind power, this is a big one, and definitely a big one in Alberta. We're seeing more and more of this all the time, and we'll take a look at some stats in the next couple of slides here. So the winds are generated by the sun as well, and it's the heating up of the air and leading to the movement of the air. So the uneven of the heating, if you think about the globe, where we have the greatest solar radiation is close to the equator, and where we have the least is closer to the poles. So uneven heating, that along with the rotation of the earth is what is going to generate the winds. So a wind turbine, like we're seeing in the picture here, these are enormous structures, by the way. So they kind of work the opposite of a fan. A fan uses electrical energy to turn the blades. Here we're using mechanical energy, the kinetic energy of the winds to turn the turbines, to turn the blades, and use that, connecting it to an electrical generator to produce electrical energy. So these are standing many tens of meters in height. Each one of these blades, each one of these in themselves are absolutely enormous. If you think about very, very large airplanes, each one of these blades are the size of, or even bigger than the length of a wing on one of those airplanes. So here in Alberta, what we do have is right now about 38 projects that are currently underway in Alberta, underway or functional. Megawatts, what they do say is that each megawatt is sufficient for, on average, about 1,000 homes. So the capacity that we had in Alberta as of December 2019 was 1,685 megawatts, and it was to be a little over 200 new megawatts in 2019, and that's a total of almost 1,000 wind turbines in Alberta. Most of them in the far southern part around Crow's Nest Pass and Crow's Nest Highway, Highway 3 in southern Alberta. If you drive down there, you will see hundreds of these turbines. Other ones are popping up in central Alberta as well, southern central Alberta. So again, just under 1,000 of them, and each one of these will vary between about 1 to 3 megawatts in terms of its capacity, maximum capacity to generate electrical energy. And again, it's 1 megawatt, which is sufficient for about 1,000 homes. But keep in mind that that's only when the wind turbines are turning, and of course that's not going to always be the case. That's only going to be the case when the winds are blowing. So quite often in southern Alberta that is the case, especially in the spring and the fall, and that's why that's where most of these so-called wind farms are located, is in southern Alberta. So yes, the wind unfortunately is inconsistent, so it's not generating electrical energy, again, 24 hours a day. You're kind of dependent upon when that wind is blowing, and that's only when that electrical energy can be generated, and it's not the kind of thing that can be stored. At least we don't have the storage capacity for that wind energy. So even though a whole bunch of it may be generated when the wind is blowing, we don't have the ability to right now store that energy for when the wind is not blowing. If you are down below one of these wind turbines and the wind is blowing and the turbines are turning, they can certainly be fairly noisy. The newer ones are not quite as noisy as some of the older ones. And again, if you do drive through southern Alberta, western part of southern Alberta, beautiful scenery with the foothills and the Rocky Mountains. So not everyone likes to take a look at those wind turbines that are interfering with, well, even in this picture here, we can see some of the foothills and the mountains. and some people do consider that to be visual pollution. Hydroelectric. This is huge in Canada as well, although we'll see not so much in Alberta. So hydro, we're referring to water, and what we're really referring to is the flow of water, and using that flow of water, the kinetic energy, the movement of the water to once again generate electrical energy. Very similar once again to what does happen in a traditional electrical generating station, whether it is for using fossil fuels or using uranium in a nuclear power plant. Only in this case, it's not high pressure steam that's turning the turbine. It's just the flow of the water that's turning the turbine. It is dependent once again on the sun, because the sun is what drives the water cycle. So taking a look at the picture here, we have the sun that's causing evaporation, primarily in the oceans. And as that water is evaporated, winds are going to move it over top of the land to a higher elevation. And then as it flows down from higher to lower elevation, so gravitational potential energy leading to kinetic energy, the movement of the water, the flowing of the water. And then as that water flows past a turbine, in one of these generating stations, that's what's used to generate the electrical energy. Many, many different examples of these. This is a fairly new one here in British Columbia, Upper Stave River in British Columbia. This one, it looks to me like this is called a run of the river, where you're not actually blocking the river, you're just allowing that water to flow. And as it flows past a turbine, which might be located in this area here, that turbine is turning, and that's connected to an electrical generator, generating the electrical energy. Many, many larger ones. They are building a much larger and controversial one in northern British Columbia right now. But this is the largest one in the world. This one here, the Three Gorges Dam in China. Many, many magnitudes, orders of magnitude larger than this very small one that I do have in the upper picture. So essentially how it works is, at least with the traditional ones where you do have a dam, is you interrupt the flow of the water by building a dam. So that prevents the water from flowing from the upper part, which would be the river, turning it into a lake or a reservoir that is now held behind that dam. So when you need to generate electrical energy, well, that's when you open up and allow the water to flow down to the lower level. So again, we do have gravitational potential energy, because number 1 is much, much higher than number 5. It does want to go to the lower level. So as it does go to the lower level, that kinetic energy is converted into the mechanical energy of turning the turbine, connect it to an electrical generator, and generate electrical energy in the process. So a nice map here, which does show how much is currently installed in Canada and the potential in Canada as well. So this again is in megawatts. And right now we're at about 80,000 across Canada, and the potential to maybe even double what we currently do have. So where in the country is the most electrical energy generated using hydroelectric? By far in Quebec. So take a look at this number here. 40,000 megawatts, much, much higher than the next closest one, which is still fairly significant. British Columbia generates a lot of their electrical energy using hydroelectric, as does Manitoba, Ontario, and Newfoundland. And it looks like even here Nova Scotia, kind of surprising, shows kind of a big number for the hydroelectric as well. So what about where we are? Western Canada, and we'll even talk about Saskatchewan. So multiple different reasons. First of all, we don't have large rivers. Secondly, and probably the bigger one, is an economic one. We have huge resources, natural resources in Alberta and Saskatchewan, which are fossil fuels. So in Alberta and Saskatchewan, a lot of it does come down to cost in many cases. It is much, much cheaper to generate electrical energy using fossil fuels in Alberta and Saskatchewan than what it is to use other sources, including hydroelectric. Disadvantages, and this will fit into the economics as well. Once again, an enormous cost at building, especially the very large electrical generating stations using hydroelectric. Large dams and reservoirs, they do destroy habitat. You're flooding a very large area. You are converting that terrestrial habitat into an aquatic habitat by doing that and destroying what we call the riparian area, which is the area along that river or stream. This can also change the river flow patterns, the drainage patterns, so really significant impacts on the ecosystem. Biomass energy. So this one here has some connections to fossil fuels because we are burning the biomass and using that to typically boil water, generate steam, and turn a turbine. So kind of similar to a traditional fossil fuel electrical generating station. Also a similarity in the sense that there is going to be the carbon dioxide that is produced and released into the atmosphere, but some significant differences. And the big difference is this one can be replaced on a human time scale. So energy produced by the release of, so yes, it is stored chemical energy that we do have in biomass. We are using it to generate electrical energy. It can be used just to generate heat as well, and also liquid fuels that can be used in vehicles, for example. So this is the way it works. So in this example here, what we have is a planting of a crop. So that crop, whether we're using the crop directly or the waste left over from the crop, that is the biomass. So we can then use this biomass. We can use it in an electrical generating station to burn, and it does release heat, used to boil water, generate steam, high pressure steam, turn the turbines, generate electrical energy. But again, we do have this waste, carbon dioxide, that is produced just like fossil fuels. The difference here, though, is by planting of crops, that's just going to use. Plants take in carbon dioxide. So whatever carbon dioxide was released, that carbon dioxide is going to be captured again by plants and just used for the growth of the plants. So even though carbon dioxide is released, completing the cycle will once again remove it out of the atmosphere. And that, of course, is not the case, at least on a human time scale, when we're talking about fossil fuels. So sources of biomass energy, what could we use? Wood waste could be used. Agricultural waste. So the picture that we have here, whether it's wheat or barley or rye, it's only the grain that we use for food, but the rest of it, the stock, that is agricultural waste that could be used. Animal waste as well could also be used for the biomass. And municipal waste. So it might look something like this. We take the biomass. We can use bacteria, aerobic and anaerobic bacteria, to gradually break it down. That could release hydrogen and methane, which itself could be used in combustion reactions to release energy. For a landfill, underneath the landfill, all of that waste, it's being broken down by bacteria as well, and it's releasing typically methane gas. So if instead of releasing all of that methane gas into the atmosphere, which is an even more potent greenhouse gas than carbon dioxide, can we actually collect it and burn it, use it to turn a turbine, connect it to an electrical generator, and generate electrical energy? So different possibilities. They are doing this sort of thing in some other cities, including Edmonton, where they are doing this with their landfill waste. Biofuels for transportation. So we certainly do hear a lot about this as well. So ethanol enriched gasoline. That ethanol does come from typically corn, like we have in the picture here. So you grow the corn, instead of using it for food, what you do is you convert it into sugar, and then that sugar can be used to make ethanol. So these reactions, they would be taking place by bacteria that are doing these conversions for us. So one of the drawbacks is, of course, is that, well, this is food. So now we're using food, which could be used to feed people. We're using it for something else, and that is to produce a fuel. So the nice thing about it, of course, is this biomass, it is renewable, whereas the fossil fuels are non-renewable, because we can just plant the crop again and generate more of that biomass. We can also use it for, so this is showing a deep fryer here. So the oil that is used for deep frying, that can also be used as a biofuel and used in some vehicles that have been converted in order to use that as a fuel source. So advantages, it can be replenished. Carbon dioxide is released, as with the fossil fuels, but we can offset that by the replanting of the crops. Disadvantages with this one, yes, well, it does still produce emissions. It can lead to the planting and overplanting of the crops, leading to soil depletion due to overuse. Huge costs, and this is maybe the big drawback. In fact, we talk about a negative energy return. It costs more energy, or it costs more to actually generate the fuel than what we would typically get out of it. And high energy input is necessary. A huge amount of energy needs to put into taking the corn and converting it to the ethanol than what you would get out of it. Negative energy return is what we talk about. And just a little bit here on fuel cells. We also hear a little bit about fuel cells. Kind of again works to use it as an analogy, a battery, or with what we saw previously with the solar panel. So what we do have is a separation of charges, negative charges here, positive charges here in a fuel cell. In this case, the fuel that is going in is hydrogen gas. We'll see where that can come from, and oxygen just from the atmosphere. The only thing that's being produced is water. So we have no chemical wastes that are being produced, at least by using the fuel cells. It's only the water that is being generated. And this is just showing one of the wafers that would make up a fuel cell. So possibly using them for transportation. So some buses are now using fuel cells, transportation, other vehicles potentially as well. So the sources of hydrogen, where can it come from? From the splitting of water. So electrolysis of water can generate the hydrogen. So this is kind of nice as long as it's coming from renewable resources. But if you're using fossil fuels for electrolysis and splitting the water, then you have a whole bunch of emissions that are coming from the burning of the fossil fuels. So yes, if we are using the fuels, then we do have carbon dioxide emissions that are associated with that. So other problems related to the storage and the transportation of the hydrogen. Infrastructure is not in place for storing and distributing the hydrogen to vehicles, for example, and definitely fuel tank size limitations. They need to be much, much larger than for a liquid fuel. And just kind of an interesting one here. This is a solar tower. So many tens of meters or even hundreds of meters high. All these glass panels at the bottom, this is essentially a greenhouse. So what's going to be happening is solar energy is coming up and it's going to be heating up the area inside of that greenhouse, and hot air rises. So that hot air is going to be rising up through this tube that we see here. At the top, we would have a turbine. So that hot air that's rising up would turn the turbine at the top, connect it to an electrical generator, and again use that to generate electrical energy. And this is the turbine that we see spinning at the top there.